Let me just start the presentation proper by thanking your team for giving us this opportunity to work on a very interesting NLP problem. I'll speak a bit more about why I found it particularly interesting, but thanks again for that. Second place solution, just to make sure that everyone's in the right call. And it's just a solo team this time with myself. You can call me by my first name, Chun Ming, or by my initial CM. And as Julius mentioned, I am Singaporean, calling in from Singapore. In fact, I just went from my second vaccination today, so a bit woozy. Hope you forgive me if I'm not at 100% right now. So in terms of the agenda for today, quite straightforward. I have about 10 minutes worth of slides. Of course, if you have any questions from me at any point, please feel free to stop me. I'll start by quickly walking you through my personal background, summarizing the approach I took, as well as the way I trained the solo AI model that I used. In some ways, the most important slide for this presentation is what didn't work. And I'll finish things off by summarizing 3 key takeaways, at least that I took away from this competition. So my personal background, I've been all over the place. I am actually an NLP data scientist right now, and do have a computer science background, studied it in CMU. But for a short while, I spent some time in the business world, having done an MBA, and joined the dark side for a while, working as a management consultant at McKinsey. But in terms of this competition proper, I think the most relevant experiences are, of course, me being an NLP data scientist. And in fact, me spending a fair bit of time on Kaggle working on NLP competitions. So I just wanted to highlight that I did participate in these 2 competitions, as you can see, the 2020 and 2018 Jigsaw Toxic Comments competitions. Just for your knowledge, these competitions were problems where we were given online comments and we were asked to build AI models to classify them as offensive or not. And I think that brings me to a broader point about why this Coleridge competition was interesting, is that I think you set a very, I guess you could call it ambitious, you could call it a difficult problem where, it's not just simply saying, oh, is this X or Y? You were asking us to extract strings from a very large data set. So I think, I think you probably could see in the forums, a lot of questions, a lot of concerns, but I think it just shows how challenging this problem was. In terms of the task, I'm not going to repeat what's obvious to you, but I do want to highlight a couple issues that cropped up tied to the task. So the very first thing is the data set. So I think throughout the competition, I and a lot of competitors, were struggling with what exactly is a data set. And I think for better or worse, I don't think we were ever given a definition of it. So to give a concrete example that I personally...
So just to interrupt,
sure.
There's a core challenge, which is there's no really good definition of a data set. So we kept saying a data set is whatever a researcher calls it. So there's a fundamental ambiguity about the underlying latent construct.
I think that's fair. And I think it was interesting because I also noticed a lot of teams were spending a lot of time on platforms like data.gov, right? And there were lists of what were...
That missed the point. That's exactly right.
And I think I mentioned this in my write-up. I just felt that was beside the point. And yeah, I did not spend any time on that. But to give a concrete example, so something like this IPCC, right, which is a climate change initiative, I think 2 different people could argue about whether it's a data set or not. So that's something that I think all teams struggled with. The second point I wanted to highlight was in terms of the metric, and this is just for more for how the team structured their final models, which is the fact that you set the F score to have a beta of 0.5, which in theory meant that false positives were penalized more than false negatives.
And that was defined by the needs of the use case.
Sure. I think that's the interesting thing is that what I found with my submissions at the end of the competition is that it turns out that the one that I set to be what I considered more conservative, my final submission, there were other submissions which were, I guess, more liberal in terms of predictions actually ended up doing better on the private leaderboard. So I thought that was interesting, at least from my models. And the third, and I think this was great, is just in terms of the sheer volume of data that you provided us. You provided us, I think, about 14,000 papers in the public training set, which were partially labeled. And I think that was just helpful in terms of, because there was an overlap with the public leaderboard, I think it was helpful in just being able to look at these papers, work with them, and then see how the public leaderboard reacted. So in some sense, that was interesting. And again, I think this was a very ambitious task just compared to what Kagglers are used to, at least for NLP competitions. And I think you can just see in terms of the spread of the leaderboard, like usually for a lot of these NLP competitions, you see a very small margin between competitors. But I think, as you can see, I think even within the top 10, there was quite a large margin. So I think that shows that there's potentially a lot of work to be done to further improve this thing in the future. I guess this is the key insight, at least for me personally, which I guess may be obvious, may not be obvious, but after spending a lot of time looking at the data set, the papers, is that, there's a certain formal academic writing style that's used in academia. You can see in the gray text box an actual excerpt from a training publication. And what I noticed is that there's just a certain formal way that data sets tend to be referred to. So I have 4 examples in the 4 paragraphs. The first one is this, what I'll call long form acronym format, which is, for example, in this case, highlighted in bold, Baltimore Longitudinal Study of Aging, parentheses, BLSA. That's sort of what I call the canonical way to refer to a data set. But of course, that's not the only way. In the subsequent paragraph, you see references just by the acronym. In the third paragraph, which is probably the most common way a data set is referenced to, is simply just a long form without the acronym. And I guess my takeaway here, or my final approach, was to take advantage of the fact that many data sets were referenced in long form acronym. The last example, last paragraph, is just to show that not all strings in this format are data sets. So in this case, this TRT, testosterone replacement therapy, that's obviously not a data set. So I'll come back to this notion that a simpler model that leverages domain knowledge. Domain knowledge in this case is just understanding how data sets tend to be referenced, often work better than more complex general purpose models. And in terms of the actual final approach, it's a very simple 3-step process: search, classify, and then finally threshold and propagate. A very first step, searching, as mentioned in the previous slide, I'll search for strings in the format long form acronym using this Schwartz-Hurst text search algorithm. And the example I use is as shown in the previous slide. This Schwartz-Hurst text search algorithm, I guess in theory, you could just use and write your own regular expression algorithm. The format is quite straightforward, but it just so happened that someone came up with this to search specifically for these types of strings in scientific papers. So oftentimes it's just better to use some work that someone else has done rather than try to reinvent the wheel. And that's what I did. Second step is from candidates that have been searched through from step 1, decide whether they are data sets or not. So this is the only step where I actually used an AI model. I used a transformer, specifically a fine-tuned Roberta-based NLP model. And 2 examples here of something that would be accepted or rejected by my model. Again, the 2 examples from the previous slide, something that would be accepted is this longitudinal study. Something that would be rejected would be this replacement therapy. Third step is just to account for the fact that strings or data sets can be referenced just without the acronym. So I'll just search for the long form part of the candidate, namely this Baltimore longitudinal study, across all documents, as well as search for acronyms if they are separately mentioned in the same document. And the good thing about this approach compared to the other approaches that I tried is that it's compute efficient. It takes about 10 minutes to run inference on the entire private data set of 9,000 documents. And it's easy to manage. The sole AI model that I used was quite manageable to train and very easy to understand its output. So I think a big issue with AI models today is interpreting the results that they give. And because I designed the AI model just to be a binary classifier, it's very easy to understand its results. It's either 0 or 1.
So let me ask a question here. Sorry.
Sure.
Or Maggie, do you want me to ask at the end?
No, go ahead.
Okay. So your classifier is 0, 1, but your prediction, is it 0, 1, or is it a probability and you set a threshold?
It's a probability and it's a threshold. Yeah. And
that's what I thought. I'm sorry when you said it was, because that made it sound like a rule-based, and that's not. So good. Sorry.
Yeah. No, it's okay. I think that's a good question, and it was what's considered a hyperparameter, the probability threshold that I use. I think for the final model that I used, I set it to be 0.9.
Right.
So anything that's predicted above 0.9, I'll accept it.
Right.
So is it that you're making multiple passes through the document set, CM?
I make one pass. So the very first step is the only time, the search part of my model flow is the only time where, well, no, that's not true. There are two parts where I search through the documents. The first and the very first step where I search for candidates in this long form acronym format. And the only other time I do a search is in the third step where I just search for the long form part. So the classifier itself is not searching through the documents.
No, I get it. Yeah, but you would end up with a dictionary if you would do multiple passes. You could accumulate certainty about what is a study, what is a data set, and what isn't. So by finding multiple mentions of the same data set, right? So
that's exactly right. I've not really mentioned this because that's sort of like I consider it a side. So in the third step, the threshold. So for the very third step, so when I search a long form part of candidates, I do factor in the frequency which in the candidate is mentioned. So I think for my final model, when a data set was mentioned, I believe above 50 times across the entire corpus, I would accept it as well. So it's two thresholds. One, which is a probability returned by the classifier, and one, which is the frequency across the corpus.
Yeah.
And the interesting thing about the two types of thresholds is that the classifier is independent of the number of documents that you look at. But for the third step, yeah, I think that kind of highlights that you need a minimum.
So you've highlighted two things that are really important to us. One is the cost and the speed, and then the second is the independence of the corpus, because obviously where we're heading on this, and where we're probably going to want to pull you in about which more later, is going across a very large corpus. So anyway, go ahead.
In terms of the actual training for my binary classifier, in this case, I actually manually came up with about 5,000 samples from the training data. And if you look at the gray box, these are examples of candidates that I came up. Again, the zeros represent strings that I've labeled as non-data sets, and ones being examples of strings that are data sets. So in many cases, it's quite obvious. For example, in the third line, you can see graduation rate survey. I think to me, that's obvious as a data set. There were quite a few ambiguous candidates, so that this goes back to the earlier point about ambiguity about what a data set is. So for example, in that call box, I see a point at this curriculum and assessment policy statement. So I think two people could argue that it's a data set or that it's not a data set. And just given the heavier penalty on false positives, I tended to just lean towards labeling them as non-data sets when I wasn't sure. Good thing about this is that this approach is that the strings were short. So training the transformer is quite quick. I trained it for 6 epochs on these 5,000 annotations, and it actually took less than 5 minutes on my desktop. So quite easy to manage. Okay, so I spent about 3 months of my spare time working on this competition. I would say that I spent about 80% on ideas that didn't pan out. And broadly, I think I would categorize
Welcome
ideas
to our world.
Fine for you.
Well, I can't complain. So, I mean, in the end, I was happy to have a working model, right? So, yeah, it's sometimes just a matter of trying a bunch of ideas to see what works and what doesn't work. But broadly, the three types of ideas that I tried which didn't work were trying transformer question answer models, transformer NER or name entity recognition models, and curated data. This was more about creating the training data that I used to train the above two types of models. And I can't say for sure since I didn't have access to the annotations, but the sense I got was that any attempt to try to inject semantic context into my model seemed to worsen the performance, at least on the leaderboard. And I just think it speaks to the difficulty in terms of annotating such a difficult data set. I mean, I've worked on annotation problems before, and what you're working with tens of thousands of documents that are dozens of pages in formal language. So yeah, I guess it's understandable that the labels are noisy. Going through each of the ideas in a bit more detail, you can see in the call-out box, I think this is a broader issue that transformer models. Sorry, can you hear me?
No, I can.
Okay.
Yes.
I just wanted to point out that transformer models, they're very sexy right now in the NLP world, but they are designed for very short text, paragraph long text. So I think a lot of us competitors were struggling to try to adapt them for use with this problem where, we're dealing with publication length text. A QA model specifically, what I tried was to try to pair paragraphs of the publication with the question, what is the data set? I did try other question types, but this was the one that seemed to work the best. And what I noticed, two key points here is that frozen QA models work better than when I tried to fine tune them on training data. And the second point, which is a bit disappointing, is that these question answer models would oftentimes flag obviously incorrect strings. So something like Food and Drug Administration, in no universe would a human consider that anything close to a data set, which raises questions about what these QA models learn and how much semantic understanding they have outside of toy problems. So I think that's something that a lot of researchers are struggling with, that AI models oftentimes just don't generalize well or just behave very oddly. Similar types of issues with NER models where they'll flag obvious non-data sets. So yeah, transformer models, very sexy, but very difficult to work with. Third point, which is curated data. So here, what I tried was to select myself, curate subsets of sentences from publications to train the above two types of models. An example of a sentence I selected is the one there, using data from the National Longitudinal Survey of Youth of 1997. So, I mean, to me, that phrase, using data from XYZ, that's an example of injecting semantic context, right? Because any human will look at that and assume, that's a data set.
And I'm going to say that our priors, and we thought that everyone would end up using these as features, right, to predict. And you're saying this didn't work for you.
Exactly.
And I think it's because of the penalty on precision. I'm assuming that, CM, but yeah, it is very surprising. I'm with Julia here. Go on.
Yeah, and I was surprised myself because I think
I'm not surprised on the QA models, because actually in the conversations people were saying it was flagging organization names, because what they would look for is strings of capitalized words, and that's what they were picking up. So that was a very mechanistic approach, and I wasn't surprised that didn't work. Yeah. But this last one does surprise me.
Yeah, and I wonder whether it's less to do with the AI models, and again, back to annotations where, I can't. It's surprising. That's all I can say. So, in terms of what didn't work, and I guess I just wanted to summarize my experience in these three key takeaways. The first, which is that simpler models using domain knowledge often beat complex general models. And again, domain knowledge here specifically referred to, these data sets tend to be formatted a certain way. And it's interesting, Julia, that you mentioned that it's mixed caps. People looked out for mixed caps, but what I found was that was insufficient. Often you needed to go the next step of looking for mixed caps followed by the acronym and using an AI model to classify them as data sets or not. The second key takeaway is that the annotation methodology is often more important than modeling. Without being able to say anything about the annotation, I suspect that most teams and myself were trying to work around the noisy labels. And a third point, which applies not just to this task, but I just see it professionally, is that transformer QA models, they've been hyped up. Ideally, right, the notion of being able to give an AI model text and then ask it a question and have it answer is very appealing. But I've just not seen them perform very well in real-world tasks. So yeah, in many cases, it's just better to work with something simpler. So I think this is broadly what I wanted to cover today.